started in hard times to bring us all in, into the laughter through thick and through thin, for public power enthusiasts without and within.
I'm Paul Dockery, a Senior Manager of Energy Resource Strategy and Planning for Seattle City Light and an energy industry practitioner.
I'm Dr. Ahlmahz Negash, a Principal Resource Planning Analyst for Tacoma Power and an energy systems researcher, and of course, an energy justice enthusiast.
I'm Conleigh Byers, an environmental fellow at Harvard Kennedy School of Government, researching grid decarbonization and electricity market design.
I'm Farhad Billimoria, a visiting research fellow at the Oxford Institute for Energy Studies and a director in the electricity markets group at S&P Global.
Special thanks to our presenting sponsor of today's episode, the Energy Authority, for making this episode possible. To learn more about the Energy Authority, go to teainc.org. On Public Power Underground, we talk about the energy enthusiasm trifecta of electrification, markets, and people. On today's episode, we're discussing optimal power flow, both the calculations of OPF for direct current and for alternating current, and the possible role of artificial intelligence, machine learning, and/or neural networks as a tool to calculate it faster. First up is our segment, 30 Seconds of Theory. This week, the question for Farhad in 30 seconds of theory is, what is OPF? I'll hand it off to you, Farhad. What's OPF?
OPF is optimal power flow. And to use an analogy, so I was going to actually use an analogy to describe this one, given our flavor of analogies. It's kind of like a orchestra or a conductor of the orchestra that is basically telling which instruments to play at which time. And we've got to do this in a large-scale power grid. And one of the reasons why we have to do this in the power grid is to make sure that, number one, we get the cheapest resources online at the right times, and we get the right resources in the right locations on at the right time. So we actually need a big coordinator, which sits in most grids in the form of a big computer program called optimal dispatch. Or it's called security constraint economic dispatch. There's a wide variety of different terms for it. But essentially what it does is to maximize or minimize the overall costs in the system. It schedules different generators at different times in a way that is consistent with what the grids need, as well as making sure that we keep the grid safe and reliable and secure.
So is OPF it's the conductor? This is an algorithm that helps conduct in your analogy?
In many ways, yeah. So there's a few musicians that kind of don't sometimes listen to the conductor's instruction, and then there's few that we can't really control, like rooftop solar or so far we don't actually schedule most consumers, right? You come in, it's all on demand. You turn on your electricity whenever you want. But for large-scale generation, that's exactly what we do. We tell them when to turn on, how much to turn on, and in return, we clear them with a market price.
Okay. Any comments on Farhad's description, his 30 seconds or less on OPF, before we get into my second 30 seconds or less question for Conleigh?
Well, I think Farhad touched on this a bit, but I think the main thing to remember about OPF is that when we're typically clearing a market, we're not usually solving for the real underlying AC OPF. We're using a simplified, linearized version of it. And so I think that'll come up later today. Sometimes the machine learning techniques are maybe things we could use to try to get a little closer to that solution potentially.
So we aren't solving alternating current optimal power flow on our alternating current bulk electric system. We're solving a simplified, linearized, direct current optimal power flow problem for our AC system. Is that what you're saying?
To clear the market, right?
But
the physics has to actually work. At some point, you have to actually solve for a physically AC feasible solution as well.
Okay. Well, that's a great 30 seconds or less. Ahlmahz, you have to be thinking about how you're going to grade this, because I added a twist to this segment where you're going to grade all their answers here in a minute, since you were once a teacher. But before then, Conleigh, in 30 seconds or less, what I was hoping to get the theory on are the differences between different the words we use for our AI. So the difference between machine learning, deep learning, these are all just terms I hear and I don't know what they mean. Deep learning, physics-informed neural networks, large language model, artificial intelligence, and maybe generative AI or general AI. I'm not sure what that one means. So take it away, Conleigh. What do all these things mean?
Okay, it's definitely a lot of terms. I'll
Yes.
try to break this down in a quick way. So machine learning really just means using algorithms to learn from data to make predictions without explicitly programming. So it could be like a way to forecast from some training data set, and then you apply it to a new data set, make a prediction. Neural networks are a method in machine learning. They're a model inspired by how neurons work in animal brains. So it's a network with nodes and edges, which are meant to be kind of like neurons and synapses in a brain. When you say there's a deep neural network, what we mean there is that there's a lot of layers of that network that are each time performing some transformation on an input layer, maybe going to these hidden layers, these deep layers, and then an output layer. I hope that's good enough for the computer science people. This is not strictly my field. Then physics-informed neural networks is something that we talk about often when we have a physical system where we know something about the underlying like natural physical laws in that system, but we don't actually have a whole ton of data in our sample set. So the neural network probably wouldn't figure out those physical laws on its own, but we know them. So we're going to give it a nudge in the right direction and say, okay, you do the neural network thing, but also keep your solutions within this physically feasible bound based on what we already know. Then you also mentioned a large language model. Okay, so that's, it is another machine learning model to make some kind of prediction. So it's like a statistical model of language, of natural human language. So when it's large, meaning from like a very large data set, and what goes behind that could be neural networks, sometimes some other methods. So AI is intelligence exhibited by machines. Artificial general intelligence is an AI that can perform as well or better than humans on a wide range of tasks rather than just a specific task. So that's what we mean when we say general. Generative AI is referring to AI that is being used to create something. So, say creating audio or visual or text.
Okay, so you got to this question. I hear people talk about generative AI and then general AI, and they are different things. They're different things.
Yeah, I hope so.
ChatGPT is like creating some essay, but it's not an essay that like any human would write. So it's not general intelligence. It's just like generating.
Yeah, so general is like kind of as opposed to narrow. So like narrow AI, you might say this is a specific task it's doing. General is like it's trying to do a lot of different kinds of tasks. Well.
Oh, okay, perfect. Any commentary on those different categories, Farhad or Ahlmahz?
No, that was a phenomenal job summarizing all of those different terminologies.
And we have an interview with Dr. Kyri Baker later, and she uses this framework where it's a lot of pattern recognition. All of these technologies are effectively forms of pattern recognition, just like our brain is. Is that like a decent way of characterizing what all of this generally is? Is ingesting a bunch of data to recognize patterns, and then if you go and you go to school, you can learn about the physics, and then you can be a physics-informed pattern recognition as a physics-informed neural network is kind of the analog there. Does that seem right?
Yeah,
I think that's pretty close. Oh, sorry, go ahead.
No, I was just saying, I think that's absolutely right. And I guess there's sort of these nuances of differences in terms of whether you give the AI or the machine the answer. When they where they have essentially an answer to compare it to, so they make their estimate, you get the answer, and then they sort of compare the error term, and over time or over multiple training, they want to reduce that error term. Other veins are things like reinforcement learning, where you don't necessarily have an answer, you have a set of policies or objectives or good and bad things that the machine can, if it goes in a certain direction, it's almost like a reward and penalty system. So that can kind of almost work without having a known answer that you that you train the machine on.
And those are different like training techniques or ways to structure the way it recognizes patterns or evolves over time, I guess. Yeah. Does that make sense? Yeah. Okay. Ahlmahz, anything you wanted to get in on?
No, I was going to say that is exactly how I think of machine learning, AI, all of these different techniques. You're basically teaching a computer by giving it patterns. It recognizes those patterns and then is able to do something productive at the end of it. So that's exactly how we learn as human beings as well. You notice patterns, and then you can begin to predict what's going to happen in the future. So all that to say, yeah.
Degrees. Good. Well, I wanted, I teased this already. You were a teacher in prior work and professional circumstances. You are still a teacher, just not a teacher in the state of where you grade papers. But you get a chance to still grade the responses here. What would you give Conleigh and Farhad for their 30 seconds of theory?
So I love teaching through analogies. That's just my favorite way of teaching complex topics. You condense it down to something simple. So that's what I appreciated about Farhad's explanation. But Conleigh has a little bit of an unfair advantage because I'm actually quite familiar with neural networks and machine learning, having done that in my background. That said, I did not know the difference between, I didn't know anything about physics-informed neural network. This was my first time hearing about that. So I got to hear her explain a bunch of stuff that I know very well and something that I don't know very well. And so I had a lot of confidence in what she was explaining that I didn't know very well, because she did the stuff that I did know very well. So I'm going to have to give it to Conleigh, even though Farhad used my preferred form of teaching.
What kind of a teacher were you? You could have two students that both get A's. You know this, right? This was a thing that is allowed. You could give them both A's. Gold stars for both is even a thing. I don't know, but you're just going to give a winner.
So I believe you say, okay. So yes, if it's a winner, it's Conleigh. If I'm telling you what I liked about both, then Farhad for sure, the analogy. I think that's the way to go with complex concepts.
Okay, well, I'll work on the grading scheme for next time. So better guidance for the game.
Unfortunately, we're in this mindset of the ESSA World Cup, and there can be only one at the end. So you got to pull me out of this mindset, Paul.
Yeah, that's a good use of this segment to get us out of only one winner. This is very much great on a curve around here. Okay, well, thank you for that. I think I was benefited by the 30 seconds of theory to better understand these topics. To accommodate a longer than normal interview, we're cutting out Short to Ground this week. Yeah. We're going to take a quick break for a word from our sponsor, and then you're going to hear an interview with Professor Kyri Baker. Public Power Underground is sponsored by the Energy Authority. The energy transition is upon us, and if there's one company who has public power's back, it's the Energy Authority. TEA isn't just any sponsor of the show. They're the backbone of what we stand for, keeping the power in the hands of the people. With offices in Bellevue, Washington, and Jacksonville, Florida, TEA has coast-to-coast expertise in energy trading, RTO management, portfolio management, advanced analytics, renewable energy, and much more. As the energy industry evolves, so does TEA, staying on the cutting edge of technology to help their 75-plus public power clients maximize the value of their assets. When you partner with TEA, you're not just keeping up, you're leading the charge. Learn more at teainc.org. That's teainc.org for more. This week, Farhad and I interviewed Dr. Kyri Baker. Dr. Baker is an assistant professor at the University of Colorado Boulder in the Civil, Environmental, and Architectural Engineering Department. She holds a courtesy appointment in the Department of Electrical, Computer, and Energy Engineering and a joint appointment at the National Renewable Energy Laboratory through the Renewable and Sustainable Energy Institute. RACI, I think is the way you say that acronym. She's a returning guest on Public Power Underground, making her third appearance. Hi, Kyri. Welcome back to Public Power Underground.
Thanks for having me, Paul and Farhad.
Yes, it's wonderful to have you back. Farhad, how well do you know Kyri?
Well, Kyri had given a great lecture at my in my lab group about I think 2 years ago now,
Yeah,
during the midst of COVID, and folks really enjoyed that, and then since then I've been following a lot of your work. So consider me a big enthusiast.
I appreciate that. And we also have a mutual friend, Dr. Constance Crozier, who
Oh
also went
yes,
to Oxford, who was my postdoc here at CU Boulder. And I think
yep,
the reason I gave that seminar to begin with, possibly. So
yeah, absolutely. You know, and I think Constance is now at Georgia Tech. Is that
yeah,
right?
she's an assistant professor at Georgia Tech. So really proud of her.
Fantastic.
So Farhad, are we going to end up losing you to some assistant professorship, or are you going to stay in kind of
I don't think
industry
anyone will
at
have
SMU?
me.
I'm sure that's
Unbelievable.
not true.
I'm sure that's not true as well. Okay, well, I'm very excited about this conversation. Farhad pointed to you specifically in talking about this topic, so I'll let Farhad take it away.
So on Public Power Underground, we get unique and diverse perspectives on the energy industry, and get folks to really share their area of enthusiasm. Kyri has done a lot of work in power systems and in a number of different areas. The area that we wanted to focus on in this podcast was on the use of AI and machine learning, and you know that is such a big field itself. And I guess you know, one of the things that we wanted to do was maybe sort of keep it digestible, narrow it down a little bit. You know, we've sort of talked. You sort of see the chat about AI being, you know, the next sort of, you know, savior of the human race, all to the other end of the spectrum of being the, you know, the potential, like you know, like a threat, you know, existential threat.
We've all seen the Terminator, existential threat,
yeah,
right?
exactly. So it's sort of now all coming to reality, and we're all seeing it every day. Obviously, in the energy system, it's a pretty specific application. But how do you, I guess, you know, just as a sort of some introductory comments, how would you frame this issue? You know, you've obviously done a lot of work on it. You actually know the field really well and have done so many great papers on it. It'd be great to just get your perspective at a high level of where you see this, you know, how do you see this playing, this concept, this thing that we now have at our fingertips?
Yeah, I think you summed it up really well. There's a lot of opportunities and there's a lot of things to be afraid of. And I'm not going to lie, there are a lot of things to be afraid of. Even, you know, within power systems and energy, there's a lot of things to be afraid of. But I think, you know, AI and machine learning isn't necessarily inherently a scary thing. It just means taking a bunch of data, learning from the data, analyzing patterns, developing predictions. So from that lens, you know, ISOs, I think, are already using machine learning based forecasting models that aren't, you know, mission critical situations, but that allow them to use historical data in an efficient way to predict future system states. So going from that to sort of my work, which is, can we actually operate grids using AI, is a big leap, but I also think it's worth exploring. And I'm personally really excited about, you know, a game-changing solution to operating grids, because we really need something like that to integrate high levels of renewables.
So in this framing, you do put it on a game-changing tool. Like this could be a game-changing tool for power systems.
Yes, because at its core, and let me rephrase, operation of power systems. So there's some things
even
where,
more controversial, even operation of power grids. Yeah, go. Sorry, I didn't mean to cut you off.
Well, I mean, like things like planning and stuff, I think you could use AI to narrow scenarios down that you're analyzing for where a resource could go or something like that, or where a new transmission line should go. So those aren't as mission critical, but operation, you know, you can have these AI assisted techniques, which I sort of tout, because you're not replacing what the ISOs are doing. You're just helping them speed it up or helping them make it more accurate through the use of data. And so now we have computing power that can handle large quantities of data and help make traditional processes just faster and better.
And before we move to the next one, Farhad, like, and you also mentioned pattern recognition. So is that really the thing that this is good at and can be really helpful to the power grid operations? Is we have patterns, and this is really just pattern recognition for prediction? Is that a framing?
That's kind of how I've been thinking about it. Is a lot of these problems are sort of utilizing historical data to look at things like patterns or things that have happened in the past that we can now predict in the future. Where AI doesn't really do a great job always is during these situations that we haven't observed in the past. So for example, like Winter Storm Uri, that wouldn't have shown up in a data set that you're training a machine learning model to predict power system failures. So that is an area where you kind of want to fall back on very heuristic but very reliable solutions and not use something like AI.
Is there also a trust issue at the moment, or do you think that like, because I'm thinking about, at the moment we've got billions of dollars of financial flows and big, heavy machinery and a lot of operations kind of following algorithms and our most of our market clearing is on optimization software already. Is it necessarily a big leap for folks to kind of go down the path where AI is either guiding or improving the accuracy, or sometimes maybe down the future it could actually be setting the price or doing something even more direct? Is there still a bit of a trust issue? Do we need to kind of explain AI a little bit more to participants who presumably still have a level of sophistication, but also consumers? I think it's a big landscape.
Yeah, there's a huge critical mass with the way that things have traditionally been done with things like determining prices, for example. That's a good example. It's definitely not perfect. If you were to go back in time and say, hey, here's how we're going to determine prices. We're going to create this very simplified model of the grid. We're going to ignore the losses in the lines, and we're going to estimate them later and tack on that as a separate price and do all these little, out of market adjustments and other things. It doesn't sound very efficient at all. But it's what we're used to. It's what, large utilities, trading firms, generation owners are used to dealing with. So we've adapted accordingly. If you integrate something like AI that maybe determines more accurate or representative prices to deliver electricity, I mean, objectively, it possibly is more market efficient. But on the other hand, it's going to be a huge paradigm shift for all these entities. So you're going to need to do it in stages. There's going to need to be like an easing in period where the prices are determined with the more accurate model, but the utilities and other entities have a chance to adapt their strategies, for example.
So we aren't just going to do a trust fall. There's going to be some like trust gating. There's going to be like, we're going to have gating steps to build trust along the way.
I think so. And I think that's not only just for their benefit, like financially or in terms of trust, but it's also, we're operating a physical piece of critical infrastructure. So if we don't make that transition gradually, bad things might happen to all consumers, not just players in the market, for example.
Yeah, I think it's definitely, and operators and participants are using AI today in a variety of different things as tools to guide them in decision making. It's sort of always for me is that as soon as you hand over control, like we've all got the sort of the rise of the bots kind of fear in the back of our heads, or Matrix, or whatever you want to think about it. But
the Mitchells versus the Machines
seems like a step.
Have you all watched the Mitchells versus the Machines yet?
I have seen one scene from it where Furbies are attacking the family, because I love Furbies.
Yes, there are Furbies in it. It is a great movie. I cannot recommend it enough. But also, yeah, it gets into the mental model of like AI attacking the world. Sorry, Farhad, I cut you off.
Yeah. And then maybe because before we also move into kind of some of the more specific work you've done, I'd be interested in your perspective on. So I think ShiftKey did a really good episode. I think they just released it on the demand that AI will have. We're not obviously going to dive too much into that for this one, but what are some of your perspectives on that? I mean, it seems like there's just big weight of growth in demand that has never been there, and has potential to be really flexible and all these great things. But then also there's just this big chunk now that we haven't really thought about, operators haven't really thought about, planners haven't really thought about. Is that something we can get up the curve on easily, understand how this demand is meant to play in the system?
Yeah, I mean, that's another big sort of change that wouldn't appear in historical data if you were to train an AI model, this huge shift in demand where it's located and also the quantity. I think one important distinction with that, though, is when we talk about using AI in power grid operations, or we talk about using AI for forecasting, it's not even remotely on the scale that, say, ChatGPT or other large language models are. We're not teaching something the whole human language and history of literature and geography. It's like we're training the model to operate this one particular portion of the grid and control, 1,000 assets or something. So it's a fundamentally different problem that's not really creating the same level of demand as these other fields. That said, the power grid has to adapt to what these other fields are doing. And so I personally, it seems like there's two camps in this. There's the people who are extremely afraid that these data centers are going to do something bad to the grid. And there's people who are like, it's a drop in the bucket. And of course, like most things, the answer is somewhere in between, where in some areas it isn't going to be a problem and in other areas it's not. So hard to say. Am I concerned? I am mildly concerned. But I'm mildly concerned about most things happening in the grid because I think about it all the time. So we're going to adapt. We're all smart and we've adapted to a lot of things. So I think we'll adapt.
Yeah, very optimistic approach. I also, your take that the problem we're talking about today is a very small computational challenge. One of the things I love about your paper, which is a great segue to our next question, is it talks about how you're doing this with like your MacBook. Like you're training a data set and running a data set with your laptop computer. And I thought that was a really good, just kind of understanding this is a really complex problem, but ultimately, if you're using these tools, it's not high processing needs.
Yeah, and I try to emphasize that because I get that question every time I present this research of like, you're worsening the problem by training more models to solve these power system problems. I'm like, listen, I used my 2017 MacBook Pro locally. It was a neural network with one hidden layer. Like the scale I'm talking about here is completely different than the scale that the media puts forth for what AI is. So that point I do want to make clear.
Yes, and also a great segue.
Because as I understand it now, a lot of the operators, in terms of emergency preparedness, kind of, have shifted. I know, AIMO was looking at this a number of years ago, basically in an event of some sort of event on the power grid or with systems to be able to actually run the grid on a laptop. So, the fact that something can be transportable and tractable, even without these massive machines that we're kind of relying on sitting in the cloud somewhere, I think that's a real, a real game changer. Again, it's something that it's kind of like when we probably all started doing, the big advances in sort of mixed integer optimization and linear programming, and we could just get, thousands and millions of constraints and variables solved in, 0.5 or whatever that second is. But potentially this is even bigger. This is something which can take these really hard problems to sort of, to a tractable level.
Yeah, definitely. And I think there's also a good point in there about cybersecurity. It's like the more we rely on cloud computations or the more we're relying on external data centers to train our models that we then use to operate physical networks, the scarier that is. So the more you can do locally on local compute, the better. And thankfully, a lot of these models, aren't at this scale where you're going to need massive supercomputers. And a lot of these can also be trained offline. So it's like you can, use slower computing power because you can take a couple weeks to train the neural network. It's not, something that needs to be done today because you're OpenAI competing with, another LLM resource.
I think that's a really good segue to kind of push into the paper and also the work you've done subsequently since then. So I guess the paper that we were talking about was a 2022 IEEE transactions on power systems paper, and it's a great paper because it's sort of 4 pages or so, but it's actually really powerful in terms of just the message. And you lay out the case for using machine learning to solve these really hard AC alternating current OPF, and maybe I'll get you to talk about maybe a little bit at a high level what it is and explain some of the challenges. But one of the questions that you put to this was, can we find a solution to the AC OPF without directly solving it? And this is something that we currently really simplify the problem. Really, even in operating grids, and market operators do this. They probably adopt different levels of sophistication in terms of simplifications, but at the core of it, they're still running a direct current optimal power flow, which is a very linearized, simplified version of the real network. So can you talk maybe to start with, maybe at sort of taking it at a basic level, what you did, and some of the, just at a high level, what the problem is and the motivation, and then maybe some of the techniques, and with just being aware, I guess, with people with different levels of familiarity of the underlying techniques as well.
Mm-hmm. Yeah, so I will also note first that paper, I think, was published last year, but I submitted it, I think, 3 years prior to that. People did not like this topic, so it took a long time to get through peer review. It was very, very, when it first came out, like, you can't replace an optimization problem with a machine learning block. No one's going to want that. And so it was a radical idea that a lot of people still don't like. But the core idea is, so grid operations traditionally, especially in areas with markets, solve a large optimization problem in order to figure out, the most economic and reliable way to match supply and demand. Now, most economic and most reliable is debatable here, but that's kind of the goal of the grid operator. And so the true optimization problem that they would solve is this highly nonlinear, super complicated, hard to solve in real time optimization problem. So traditionally, what has been done is we make assumptions in order to solve it. So we pretend the lines don't have losses. We pretend there's no reactive power. We pretend all the voltages throughout the grid are the same. It's actually amazing and shocking the level of simplifications we made, and the grid is still able to operate pretty reliably because there's just so many layers of redundancy, making sure that the market decisions don't impact the physical system too much in a bad way. So they solved this simplified problem, which, Farhad, you call it the DC optimal power flow problem. So it's not like we're solving a direct current network because it's still AC power flowing through the lines, but the DC moniker comes from the fact that it's a linear system of equations, and it represents things that happen in linear circuits. So I was thinking about this over, when lockdown orders first happened in 2020. I was in my house in my pajamas for days on end, sitting around, being bored, thinking, wow, for my whole career, I've been doing these simplifications of this optimization problem, trying to make it faster, trying to come up with smarter ways of simplifying it. What if we approximate the losses, or what if we linearize only this portion? There must be some kind of game-changing way to actually solve this thing fast, rather than, all these little things I've been doing. So I was thinking about machine learning, which my master's was in. So I kind of switched fields completely. I was doing computer vision for facial recognition and for stem cell division. That's what my master's was in. So I was sort of familiar with all these machine learning ideas, and I started thinking about them again. And I was like, wait a minute, we have a lot of historical data in the grid, and we can also generate a lot of different scenarios offline, just run the grid models that the independent system operators have, and go through this wide variety of scenarios that could happen. Can we just train a model to learn the current state of the grid and map that to the optimal way of operating power plants? Instead of solving this massive problem every single 5 minutes, it seems so inefficient. Not that much changes every 5 minutes. So then I tried it on a very simple problem. I texted one of my friends who works at NREL. I was like, do you want to explore this with me? And he was like, okay. So we tried it, very simple, and the results were pretty amazing. We were shocked at how well, even this very basic machine learning model was able to learn the solutions to these nonlinear problems. So then I built it out. I simplified the network, actually, and that's the one in that paper. It's not even a deep neural network. It's actually a shallow neural network trained on my laptop, and it still was able to emulate the solution of these large, expensive optimization solvers, just with these open source packages. And we were able to solve the optimal power flow problem in milliseconds. So it's extremely fast. The caveat here, it doesn't work when you have a discrete change in the grid, like a generator goes offline or a generator comes online or a line goes out or a line is reconnected. That fundamentally changes the space of the problem. And so you would have to retrain the model on a new set of data that represents that space. So that's a big caveat. There's researchers working on that problem, but it's something that hasn't robustly been solved, basically.
Sure. And I guess maybe to understand that a little bit more. So when you say, and you know, I've come from optimization land, and this, you know, still to much of the extent machine learning and AI is still kind of like new to me in terms of the techniques. When you use AI or machine learning to solve a problem, it's making an estimate, correct? It's trying to find something which is in based on its learning would be its best answer, you know, best guess kind of thing. And then are you using, so my understanding is then you're using this sort of optimization. Once you have this really good estimate, you're sort of right near where this optimal point is. And so it's not that long to then walk down the path and find your, you know, your minimum or your maximum or whatever point you're trying to seek. Is that right?
Exactly. So we're not replacing the whole optimization problem with a machine learning model. We're getting the solution really, really close to where it needs to go, because it's very hard for a neural network performing regression to satisfy all the physical constraints of a power grid exactly. It's like power into a bus has to equal power flowing out of the bus. The neural net's going to get really close to that, but satisfying that equality with exactly left-hand side equals right-hand side, extremely hard. There's ways you can do it. It increases the complexity of the machine learning model, which is fine. We've also done stuff like that. There's smart tricks you can do to embed actual constraints into the neural network. But what we decided to do instead, if a grid operator is actually going to integrate this in with their system, they're going to want to use their existing tools somehow. So the AI piece of it gets the optimization extremely close to the optimal solution through this approximation, through this prediction. And then you feed that solution into the conventional solver that the ISO may use. So like one of these existing software packages that's been vetted for decades that operates real grids. Taking in that starting point for the optimization, all it has to do is a couple iterations of a conventional optimization, and you're at the true solution where it satisfies all those hard equality constraints. So that was the idea. You know, you sacrifice a few seconds sending it to a conventional software, but you've sped up the majority of it down to 10 milliseconds. So it's AI assisted optimization, I would call it.
Yeah.
So
and that's a game changer, really, isn't it? That's sort of,
that's what I say.
Well, yeah.
Well, it sounded like when I was reading through the paper, it sounds like you're basically doing that with the DC optimal power flow today. You're using it to get close to the solution and then handing it to the same optimizer to get to an AC solution for the power flow. And basically you're just replacing the abstractions of DC OPF with an AI approximation of the answer, but then you hand off effectively at the same point, you have to go actually resolve through a post-processing step anyway?
So yeah, there's two things here. So conventionally,
two things, thank you.
There's two things. So you're right, like a very common technique is to solve a simple DC linearized problem and then use that to warm start the true AC solver. That doesn't get you as close because the DC approximation is still in some cases very far from the true AC approximation, especially if you're in a network where the losses are very high. But there's also another thing that grid operators do, which is in markets, which is where they'll solve the DC OPF to clear the market. They'll run an AC power flow. So not an AC optimal power flow, an AC power flow, which nudges some of the variables into just something that's physically realizable. So it's not getting an optimal solution to the true nonlinear problem, but it's nudging the DC solution into something that's at least physically realizable.
I think that's a really important point there.
Tease it out, Farhad, because I don't know that I got it yet. Keep tease it out.
I think you're on you're on that mark. We're kind of down that road because I think so. My understanding from working at the operator in Australia is that we've got all these linear programs right now, all these linear constraints, and they're informed by all these offline regressions that are run by the transmission networks that sort of provide this window or constraints of security. And they say, hey, look, we've done all these regressions, and based on this is sort of the linear equation and constraint that you're going to use to bound it. But of course, they're not necessarily, that doesn't guarantee security. There's still, and especially now because you've got all these different control systems and different resources integrating and changing rapidly, you can't necessarily guarantee that. So I think something like this, where you are incorporating everything into the problem to day one or second one or millisecond one or whatever, is a different approach. And to get to a point where you can kind of get to a solution there is I think different. But also one question which I did have here, and we're spending a lot of time on this problem because I think this is a really good one. Do you think that as a starting step, like I know that a lot of the operators, especially those that have either day-ahead markets, currently still have a pretty hard problem to solve. It's a a mixed integer problem where they incorporate the startup and shutdown, essentially no unit commitment of different resources. So those problems are also not convex and they're pretty hard to solve. I think something like Euphemia, which is the European one, clears it in about 11 minutes. But still, could machine learning be also used in existing market dynamics or market clearing? Can that also be used to speed up, or is it something which, in your view, is more restricted to the sort of the AC type of problems?
No, it could easily be. And I think actually the results for mixed integer linear programs, like learning the solution to those, the work there is even more robust. So it's, I would say, harder to learn the solution to a nonlinear program, even with those integer variables. So if they can do it within 11 minutes, that's not too bad at all, especially for a day ahead market. But the real benefit with the day ahead comes from, instead of solving one problem, maybe you solve a wide realization of problems, like thousands of different loading scenarios, weather scenarios, solar scenarios. And then you see, is the system truly going to be secure, whatever percentage of the time the grid operator requires, depending on which realization actually happens. So one big advantage of the machine learning approach, even in these day ahead settings, is the ability to run such a wide range of operating scenarios and check that everything's going to be okay.
Could you see this as a stepping stone to like a stochastic unit commitment problem? I know that's something that a lot of other researchers have spent time on and talked about. Like,
Paul seems excited about this one. I don't know why.
I mean, stochastic look ahead unit commitments. This is a whole, I'm a Bayesian and a Bakersian, and y'all, this is to be great for me. I love these things.
Yeah, it would definitely, that's exactly the type of problem I'm talking about. So with those stochastic problems, it's like, if you were to run a Monte Carlo analysis where you sample from all the distributions, it still takes a really long time. So in a lot of these stochastic problems, you'll simplify it down to like a few representative scenarios, or maybe the expected value of some of the uncertain variables. There's other techniques too, but being able to run just the normal problem with different realizations of these variables, I think would be really valuable, especially for even planning studies. It's like if we were able to do a capacity expansion planning study with a high fidelity grid model rather than these simplified, network flow models, there's also a lot of value in that. Hopefully it makes investment decisions, more accurate and more profitable, et cetera.
Yeah, this is a great segue to the next question. Also an area of interest for me, because part of using a heuristics of like how the grid has operated in the past to inform a model is one thing, but when you can start projecting out for future conditions that are not reflective of what we've seen in the past, which is what we're experiencing now with different resources on the grid, I find that you can use the physics-based calculations, the engineering calculations from first principles, do robust multiple analysis using supercomputers or whatever, but then just find patterns with your machine learning. That to me is, and I'll let Farhad take it away to the next question, but I think that's to me where the future opens up future solutions and fast solutions. which is why I'm interested in the next question.
Yeah, and I think this kind of goes to some further work that you've done as well in this area of system security and physics-informed neural networks. And I think security, I mean, to me, this is, because it's such a highly technical and an engineering issue, as well as, it has economic implications too. But as we move to a fundamentally different grid, this is why people like talking about resource adequacy and networks, because it's high level, we can kind of get our heads around it. I think security is one of the biggest risks out there. And as we see markets evolving quickly to low carbon, I think this is one of those big risks that are just sitting there that we kind of need to really get our head around in terms of understanding, at the very first level, trying to make sure that we're not running afoul of these sort of conditions and physics constraints. So this work uses, and again, it'd be great to get your framing of this, but in one of the things about security that when I've looked at some of the engineering of it's much more complicated because it involves the interactions of different control systems. So, a big thermal or coal unit will have a different type of control system. Power electronics, wind, solar, batteries will all have different types of electrical control systems, and they can be described by these differential equations. And I think those are much harder to kind of integrate into a solve and solve for that. And so it'd be great to get your understanding of how machine learning can help with measuring some of these variables. These are really important ones, where voltage and power angle and things like inertia. So maybe if you could just frame that a little bit and kind of talk about what the focus of some of your work in this area is and where you see it going.
Yeah, I think when we start talking about things like dynamic system stability or inverter-based resources and what they're doing to frequency regulation and security, it gets a lot more complicated to apply AI, because at the end of the day, we don't necessarily want to spend a lot of time and money pursuing the best solution to make the system stable. We just need the system to be stable. And so, for example, a lot of inverter-based resources, they'll have droop curves that are hard coded into there that say, if the local voltage changes by this %, change your power injection by this other %. And so far, those like very linear proportional control rules have been working for distributed energy resources. At the large scale, when we get a bunch of these on the system, there could be situations, and we've seen this in the lab at NREL, where you actually have these heuristic control rules fighting with each other. So the lack of coordination, because they're distributed, they don't have time to communicate to a centralized controller that then sends them a command for how to operate. They need to be able to respond quickly to local measurements like frequency or voltage. AI could be used to sort of bypass some of those coordination issues that may exist when you get, a ton of intermittent and inverter-based resources en masse connected to the grid. So I don't think we've seen a ton of issues there. There have been some, but not a ton yet. But I think in the future, it's going to become more of a problem. And so you'll see ISOs just have a bunch of layers of ancillary services ready to go. And I know Australia is a little different. Australia is a very dynamic market, but these different layers of regulation services and reserves, capacity, et cetera, they're all kind of aiming to solve the stability problem on the fast time scales. So AI can definitely help there make that problem a bit faster. So what we've done, and we should have a preprint out pretty soon, it's a very exciting topic, is you can actually combine the optimization piece with, steady state power flow, clearing the market, determining prices, with the stability piece. So we want to replace those heuristic droop controls or heuristic ways of ensuring system security with optimal ways of doing it. So we were exploring that problem with physics-informed neural networks and what's called neural ODEs, which are another similar architecture that is able to embed differential equations into the neural network. So being able to solve those things quickly, embed the equations directly into the machine learning model, I think there's a huge exciting area there for research and for practical applications.
I feel like maybe this is where y'all are over my head a little bit. But to kind of get back to what I do understand about system security is the value of the big spinny things. Like the big spinny things is really valuable. And part of what we do with reserves is like we keep the big spinny thing spinning so that it will maintain our frequency on the grid and have some inertia for these response. So is part of what you're thinking about here is as you get less of those, there are ways to embed the kind of dynamic response within like inverters in the field instead of trying to have a central control to those, because central control will never be fast enough. I don't know if that's true. Will central control never be fast enough to get the same reliability and
That's a good
frequency response?
That's a good question. I don't know enough about wireless communication to know the answer to that. But I mean, so what you're talking about is like this virtual inertia problem is, can the inverters emulate the inertia of the large spinny things? And there's a lot of people working on that. It seems to be working well. I know less about that area of power electronics, but I still think there's an opportunity for AI to look at the control piece of that. So not the power electronics piece, but the control piece. Like given this local measurement, how do I decide how to control my variables within my inverter or my battery or whatever resource I'm looking at that isn't a large conventional generator? So the physics informed piece of the neural network is basically you're embedding equations that actually describe the physical interaction between variables into the neural network. So it's not just taking historical data and learning the mapping between input and output, it's embedding the relationship between input and output directly in the neural network.
On the devices out in the field. So on the solar farm.
Yes, ideally, yes.
Okay. And you made a distinction there that would be helpful if I could tease it apart and understand it better. The distinction between like a grid forming inverter who is like synthesizing the inertia of the physical thing versus what you're talking about here. And I don't understand the distinction. And I don't know if I'm missing something.
I guess what I was more thinking about wasn't frequency. I was more thinking about voltage, just because inverters do a lot of volt var control locally with these droop curves. The virtual inertia thing is a totally separate topic that I'm less familiar with. So I don't feel comfortable talking about it as much and how AI could be used to emulate inertia.
So that in itself is the inertia helps with frequency, and this is more about voltage. Maybe that's helpful enough for me.
That is true, but changing the power output or consumption of a distributed energy resource, for example, still impacts the frequency. So there's still ways that you can adjust frequency without necessarily having a grid forming inverter.
Okay.
I'm really glad that voltage has been mentioned, because voltage is sometimes the forgotten cousin in discussions of power system security. And I know it's something that, again, grids that have gone down this path of a lot of electronic. I think Texas is starting to go down 60%. I think was the recent record of inverter-based generation or renewable generation. And inertia is one of those things that's been talked about, because we can kind of understand, frequency again has been something which has been talked about. It's a central measurement, and we kind of know, okay, these big spinny things, there's a kinetic energy associated with the mass that kind of injects this energy when you have a frequency disturbance. There's also a voltage sort of effect that these big spinny things have had, and partly related to the inertia, but partly not. But the fact that it has had this sort of suppression effect of voltage has meant that when you get a voltage slip or when you get a line trip or something like that, it actually smooths out those changes. And a lot of folks talk about it as fault levels or system strength or all these other sort of engineering terms used. But one of the things that is interesting to me is how you can integrate that at a controller level, and have that dynamic response. But also, interestingly enough, one of the things that people have been talking about, there's a lot of these pilot programs coming into grids, how people get paid for it. Do you think that AI might help in, and I don't know, I mean, maybe this is just a stretch too far for this this tool, but can it provide any way of, first of all, figuring out what different units are doing so that we can pay the right people? Or I don't know, I'm just sort of wavering into it, maybe a different topic, but yeah, that was kind of where I was going with some of this. Is people can do these things, but how do you, number one, coordinate them in an engineeringly robust way, and then two, how do you get people to, you know, to have the incentive to provide the service?
Yeah, those are good questions. And so, like, if you think about, again, the droop curves, which are basically just a proportional line where it measures the frequency change and it adjusts power output. Those are, you know, hard coded into these generation or sometimes battery resources. So if you have a bunch of them responding in an homogeneous way, that could cause the frequency to spike too much. So AI could be something that's a little bit more adaptable in a fast way to, hey, I'm noticing that, you know, the frequency is increasing or the voltage is increasing. My actions don't seem to be moving it in the right direction. Can I change how I'm performing? More so than like conventional control systems, perhaps. Now, I'm not fully confident in that statement because I haven't tried this myself, but one thing we have done is we've looked at distribution grids that have like high penetrations of solar, and basically the solar inverters that are near the end of the distribution grid where the voltage is the most wavering, you know, it's the voltage is stiffer close to the substation. The voltage wavers a lot closer to the edge. Those inverters participate in voltage regulation significantly more. So it's sort of like, should those consumers be compensated for something just based on the fact that they're in a physical location that means their inverter's been performing voltage regulation more? And I think the answer is yes. I don't know how to do that in, you know, the best way, but you see the same thing in the wholesale market. If you have a resource that's just really well placed, you make more money. And there's currently no compensation structure that I'm aware of that awards voltage regulation in the same way. So.
Yeah.
So are we going to add to our LMPs? It's not only congestion and losses, but now strength, like system strength is I don't know. I'm way
maybe
over my
because
skis here.
that system lambda part, or you know, the marginal cost part's going to get smaller as more $0 marginal cost assets are integrated. So there might be more components that are added to that LMP. Yeah, contribution to reliability, dispatchability, firmness. I don't know.
Heard it here first. I'm probably not.
Yeah,
I heard
new LMP just dropped.
So I think it was 1993 where William Hogan wrote a paper where I think it was called Markets in Real Electric Networks Require Reactive Prices. So are we finally at that?
We're finally there.
Where we get reactive. I know for markets folk that, you know, people are probably like getting really excited just at the mere mention of having a new spot price. But maybe we'll have like, you know, I think yeah, every time there's a new market, I think a lot of people start getting, you know, getting really excited. But
that's perfect. But I think we're running long, and I want to jump to the next one. Are you okay if I jump to the next one, Farhad?
Can I just, sorry, before, I know we're stretching the friendship here, Paul, but I can't let Kyri get away without talking. She just released a preprint on something which is, again, really exciting, that relates locational marginal prices with DCs, with circuit laws. Can you just briefly, like 20 seconds or, you know, just talk about that a little bit? That was, again, really, really interesting.
I was so happy that other people found this interesting. So I've been teaching, you know, intro to circuits for 7 years now. And me and my collaborator, Harsha, were trying to figure out, is there an explainable way to describe locational marginal prices if you don't understand optimization duality? So normally it's what Paul mentioned, you know, it's like these three components, but mathematically, where do those come from? And like, what causes them to become negative? What causes them to spike? We have these heuristics we use, like, oh, if there's a lot of renewables, sometimes it's negative congestion can cause them to spike. but sometimes congestion also causes them to be negative. So they're really hard to understand. So I was taking a look at these and I was like, there must be some way of interpreting these. And I noticed that it looked like the Kirchhoff's current law that I teach, current flowing into a node, then splits into current flowing out. And I was like, prices can't flow. This is just me teaching this class too many times and seeing things. But then I worked it out and I looked at the actual equations and I was like, wait a minute, no, this is exactly Kirchhoff's law. It's in the constraints. And so then I was like, well, there must be an analogy for like voltage sources and current sources. And so eventually the analogy took place. And there were multiple points where I was like, it doesn't work if there's, X in the network or something. But no, it kept adhering to the analogy. So congested lines are sources in the DC circuit. Lines are resistors, like normal. And the topology is the same as the topology of the grid. And you can literally see, the sum of voltage drops around a loop is 0, Kirchhoff's voltage law. The sum of price differences around a loop is 0. The prices at one node flow into adjacent nodes in a specific way, just like Kirchhoff's current law. So it was a really interesting thing. Is there utility to this? I mean, there's definitely educational utility. I don't know if there's a lot of utility outside of that, but I think that alone really helps people understand pricing, how pricing work and how prices can be negative and how prices at adjacent buses are related. So a lot more people understand DC circuits than understand locational marginal prices. So that was something that we're really excited about. We have a follow-on paper coming soon, expanding it to, I won't say too much because I'm also very excited about that, but expanding it.
Okay. We will see this with bated breath. Look forward to that.
Any follow-up, Farhad? You haven't strained my friendship at all.
No, I think this was, I mean, again, anything that can bring a new analogy to something, even folks that are in LM, I mean, I talk about it as being the dual, but heck, I don't know whether something's going to be negative and another node is going to be positive. And, so I think anything that provides an explanation of how these economic laws, I mean, this is kind of getting into Schweppe's beautiful reconciliation of engineering and economics. And yeah, it just gets me very interested and enthusiastic, as we say.
Yeah, the negative price thing alone is, I think, the most utility I've gotten out of that, because I can take a look at a basic DC circuit. I've solved hundreds of them now in class and in my life, and I can tell you whether or not there's going to be negative voltages in the circuit, or whether or not this node could be negative if this one is positive, et cetera. And so you directly translate that to LMPs. And so that analogy for me has been extremely helpful, just the negative price aspect of it.
Well, I'll use it as a segue, because if you take an element out of that circuit, it will change the LMPs entirely. And as you mentioned, in your AI solutions, when you take an element or change the elements, you have to have a whole new solution set to then resolve. And there is skepticism for AI and for machine learning around when things change, whether it will be robust and adaptive. I'm sure you get a lot, and I think you started out with the skepticism of industry professionals. So as a takeaway, one of the questions we're asking people is like, what perspective you would want to share with other listeners to this podcast, whether it be policymakers, industry executive, power system engineers who may be enthusiastic about trying to find a game-changing solution but are skeptical. What would you leave them with?
I would say it's not always a step function. We don't have to go from 0 to the whole grid is operated with AI. We can try very small little things. We can microdose the AI to start with, So we can try, moving from forecasting to operating, I don't know, a couple inverters, maybe something that's like a small scale, low risk way of integrating AI with the system. People will start to trust it more. There's a lot of negative press around AI being a buzzword, which it absolutely is. And that's unfortunate, because then it's kind of strayed people away from using it as a useful tool. But think about it as a tool. It's just another tool. It's a way of using data. You might as well use it, and you might as well try it. So don't be afraid. Dip your toes in the water, and AI is, at least for some things, not too scary.
Yeah, we'll talk about this with the rest of our hosts, but AI is also like this buzzword. But machine learning is something, like, frankly, every utility out there uses some machine learning software to do forecasting today.
Yeah, absolutely.
And it's
already
like,
in there.
It's already in there. We're doing stuff with machine learning. we're not going to use large language models for very much at the utility. Maybe
Yeah.
some applications. This is not that. Well, we already did some analogies here with the DC power circuits, but on this season of Public Power Underground, we're hosting this Energy System Analogies World Cup. We're going to get you to rank all the hosts' analogies and prior guests' analogies, but you have an opportunity, if you want to take it, to submit your own analogy to our ESSA World Cup for this season. Do you have one that you want to share?
I need to think about it some more, but I definitely want to submit one. And I took a look at the existing analogies. There's some tough competition in there, but I think they're all great, and I will submit one of my own.
Okay. Okay, well, you and I will have to work together because I put together these beautiful graphics about the analogies, and I want to make sure I reflect it well. So thank you. Looking forward to it when it comes. Okay, Kyri, you're going to rank it offline. You're going to share it offline. I want to say thank you for joining me. I hope you feel seen, heard, valued, and appreciated. I hope you've always felt that way when you've come on Public Power Underground.
I have. Thank you both so much. This was fun and interesting, and I hope the viewers find it interesting.
Yes, thank you. Farhad,
Thank
it
you.
was
This
great,
was
wasn't it?
awesome.
Yes.
Fantastic. Yeah.
Okay, now we'll go back to Conleigh and Ahlmahz to close out the episode. Welcome back. Now we're going to debrief the discussion with Professor Baker, with Conleigh, Farhad, and Ahlmahz. Any reflections on the interview? I'll hand it off to you first, Ahlmahz.
First of all, Kyri is one of my favorites. I'm always glad to hear her perspectives on things. And I like that you all started off with that fear versus optimism for AI. And I felt like she had a really balanced perspective. I have to admit that I teeter a little bit more on the optimism side than the fear side. So I'm constantly thinking about the art of the possible, what we could do with AI. The conversation was really a great reminder about what we can do, and the fact that we're already using AI in power systems and have been for the longest time. So I felt like she gave a lot of good examples of how we're using machine learning to improve what we're already doing in the power system. These are things.
Can I ask?
Yeah.
Can I ask you a question? Do you use it at Tacoma Power in like power planning? I mean, do you have machine learning forecasts that you use? Yeah.
We use machine learning in our forecasting, and more recently, because we have these large language models. I know you all didn't talk about that, but we use ChatGPT because we're developing our own model to our system model of our hydro system. So we're not using Aurora or Plexos to model our system, and that code is a lot of it is written by ChatGPT. So like we were able to make a ton of progress over, well, I'm saying I was not around last year, so other people made a lot of progress using ChatGPT in creating a model of our system. So yeah, we're using, and of course, with me being an energy justice enthusiast, part of my research looks at unintended consequences of policy. And I've thought about how we might be able to use AI to predict unintended consequences of policies. So anyway, those are things that we're not doing, but would love to see like a long list of the art of the possible with AI in power systems. Those are my thoughts. I absolutely love the conversation. I can't wait to have Kyri back, Dr. Baker back out again.
I was just saying, I think the use of AI is I think practically is really set to grow if it hasn't already. I think Kyri had mentioned that she wrote that paper, and I remember seeing a working paper on when it's published in 22. I believe, the paper that we referenced, but she said it'd been 4 years in the review work.
Yes, she was way ahead of the game. She was like
way ahead. Yeah.
Yeah.
And I think at that time as well, it's like she basically said she ran that model on the laptop, and that's 4 years ago, before ChatGPT and everything has sort of come into the public. So even what we're able to do today, I think is exponentially more. And I guess the interesting thing for me is we had probably couple of power grids maybe 3-4 years ago doing and using machine learning in either forecasting or other applications. Today, I think it's going to be much higher, and I think in 10 years, it's not even 10 years, maybe 5 years or less. It's probably market practice. It's standard practice to use all these different tools. And at the moment, that's kind of the main thing. It's a really, really useful tool. What would be interesting is at the point where it actually gets into setting things like dispatch and prices and large amounts of financial flows and capital investment is made off the back of it. That's going to be probably the next trigger point or the next milestone that AI hits in terms of its commonality in society and in the energy grid.
Yeah, she talked about that hybrid approach, and Ahlmahz, you mentioned it as well, where there's this distinction between what you can use for planning, which is what we use like for forecasts, and then for power systems. And the power system thing takes a different approach. Conleigh, I'd love to get your thoughts on the distinction between those types of uses and then the scrutiny for one versus the other.
Mm-hmm. Yeah, it sounded like to me the conversation was, kind of going in two directions. Like one is that there's this effect of the growth of AI in other sectors on increasing the demand for energy. And, even some of that growth could be from the power system sector. As Ahlmahz was pointing out, her team has been using ChatGPT to help in coding. So, there's demand for more processing power. So ultimately demand for more energy if we have more use cases for AI going on. So that brings up the whole range of questions about, firm low carbon resources, how we meet a large amount of new energy demand that we expect to have in the future. And then the other kind of bucket that the conversation went into was AI as a tool in power systems, right? So we've seen that certainly already, machine learning is definitely being used for planning purposes, for forecasting, thinking about future scenarios, but it's a bit more difficult when thinking about using it for operational decisions, except in cases where, Kyri mentioned that in some of these instances, we're talking about trying to solve a really difficult OPF as an optimization problem. And what we might do is use AI to help us find a closer solution to that optimal solution, right? So some warm start that's going to make it easier to solve, and that's a bit easier to implement if you're an ISO. But where it gets trickier is when using AI feels like a black box for operators, because this is a kind of system where, you really need to have to justify the benefit given the risks. Like you want to understand what this model that you're using is doing. And so there is research in that direction to try to have some kind of, sort of performance guarantees for using AI for these operational decisions. So that could look like neural network verification. So trying to, find some kind of, range of error that you would expect with that, or using physics informed neural networks. So, limiting answers to things that are physically feasible. We can link a paper in the show notes that goes into that well, but I think that's, kind of a promising area of research, is trying to take these models from being a black box to something that, you could count on more if you were going to use them in operations. But of course, you got to have good enough reason to do it. Hopefully, it's something that, is worth doing, given the tools that we already have to do those jobs.
Yeah, the worth doing, she's touched on it. We get maybe better answers faster, closer to optimal answers faster. So that's like the reason to do it. One of the areas, now that I'm back in the safe space with y'all, who I have a lot more, like I've built a relationship with you, so I feel like I can be more vulnerable. I was trying to understand, because right now what we do with DC, optimal power flow equations, is we do try to get close. We optimize that to get close to the solution, and then we nudge them to an answer with an AC power flow model. We just take what it gives you and then it gets to a resolvable answer, is what I understand the current methodology is. How far afield, or what are, like, How different is that technique where you're using a DC, which we don't operate a DC grid, but it gets you somewhere, to substituting that step with a machine learning model, whether it be physics informed neural network or some other? Like, how analogous are those things? Because when you say it to me, they seem analogous to me, and I'm like, oh sure, yeah, absolutely. Use a machine learning model instead of this DC approximation, and you probably get a better answer faster.
So the way that I would step back and think about this is that in the most perfect ideal world in which we are not bound by any constraints on processing time, our ability to solve really hard optimization problems, we would solve an AC optimal power flow problem. And we'd also use that to dispatch, the resources in the grid as well. However, that problem is just too big. It's too hard to solve with our current computational abilities. So what we usually solve is some kind of linearized form of that problem called a DC-OPF, sometimes including a bit of losses, sometimes not. In some markets like the California ISO, they actually do include AC constraints to some extent and various iterations that they have. But in all these cases, we're solving some kind of solution that is not that AC OPF optimal solution, right? We're got some solution. And then the question now is, how far off are we from that? If we are 2% off, maybe we care. If we're 0.002% off, maybe we don't care so much, right? So that's kind of the question, is like, how much better off would you be if you could find that AC OPF? And, I think that's a point that Kyri makes sometimes, is that like, maybe these DC linearizations, especially you're not including losses, really like, we're sort of abstracting away from the underlying reality of the grid. You could make kind of the same analogy to like zonal versus nodal pricing, right? That the zonal pricing done in Europe is abstracting away the grid into being more simplistic than it really is. And I think that would be a fair point. You have to ask, like, so how much improvement could you make by having like a higher fidelity representation of what was really going on? Then you'd think, okay, is it worth doing this? Is it not worth doing this? And then, as far as using, if you're using AI instead of optimization to solve or to get closer to a solution, and then using optimization in the end to find that ACOPF, how, what are the trade-offs of doing that, right? Like, there's some extra processing time that you're going to need to do that. Is it worth it for the amount of welfare improvement that you would have from finding that better solution? Like, those are the questions that would come up.
That was really comprehensive. I guess the one thing, the only thing I would add is currently, more, again, it varies for individual grids. Most grids will use, the original DC-OPF, but a much more, there's usually multiple, maybe 10,000, 20,000, sometimes north of sets of linear constraints in these big solver engines. And so the best effort has been, even when, and in the real world grid or in the real problem, you're not just doing a dynamic balance, but you're managing transient stability, you're managing small signal stability, voltage, which does reflect in the ACOPF, but there's a whole host of security constraints as well. So the current way that it tends to be done is offline constraint development by the operators, by the network owners, based on what they see, and they may use machine learning already in parts of it, but they develop these constraints and then they bring it all into the big solver. And the idea is, well, that should give us a secure system. I think what we're seeing now and more is, because of the change of interface between resource and grid, more electronically coupled inverters into the system, more variability, loads being much more flexible, that window, or that border that we put around for security is becoming less strong, or it's sort of becoming more fragile. And we're routinely seeing excursions outside frequency bounds or stability bounds that we thought were protected by this linear envelope. And so that's, I think, where solving the actual problem or estimating that actual problem is going to be much more valuable. That said, I think there's probably a bit of inertia in grids just kind of working with their engine. I know that when I used to work at AIMO, touching the dispatch engine was it was a real, like, it works. We don't want to touch it. That kind of mentality. And for some, probably for good reason. It's like, if it ain't broke, don't fix it. But I think as we move quicker and quicker to a different state of the system, we are going to have to move in there, or grids that are maybe developing a proxy or an alternative version are going to be better placed, because there's going to be this trigger point where I think the grid is going to have changed so much that you just can't linearize, or you can't create that envelope in a very effective manner.
Said another way, the abstractions we're relying on, with the heuristics of the existing system to reinforce are going away. So maybe those abstractions aren't valid anymore, and we need to actually get closer to the AC OPF optimization to get to real solutions in the future. Is that saying a similar thing differently?
Yeah. And I think also, so one of the things, particularly in grids like Australia, probably more so in places like ERCOT, is the security, the specific, system stability, system security constraints. And those are incredibly complex, because to actually model those, you need a full at the very extreme, you need a full 3-phase model. So not just single phase OPF, but multi-phase OPF, which is even more complicated and harder and more intractable. So at the moment, again, grids that are at the forefront of this are using those offline versions to inform then the linearized constraint. So potentially AI could assist with getting better solutions for those too, at least in the interim. But that, we're seeing different forms of oscillations, we're seeing different deviations out of security bounds. Those are probably the issues that operators are more concerned about, like the control rooms are really concerned about, because even when you draw a nice OPF boundary around something, there's dynamics at play, and those dynamics are harder and harder to understand when you've got different control systems. So this is, I think, where something like physics informed, where you can actually map the control system into the neural network, would be really interesting. And I think where you could get a better, more secure outcome, or a better estimate of the secure outcome as well. I think that's a real advancement that operators, I think, will be eager to adopt and use to develop anything that can improve their forecast of what's actually going on in the grid is important.
There are two things I want to dig into, and we're kind of short on time. The first is what you're talking to, Farhad, is the importance of this type of advancement in our ability to solve these problems as we get higher penetration of different types of resources. As our system changes and we need to actually resolve these complicated questions, because the new grid relies on, or can go into areas where it is no longer secure. You're losing system strength there, and you need to better manage your optimization to do that. That's one thing I just want to make sure we're aligned on, and what this can do to solve that. And the second is, she mentioned in the interview, and Ahlmahz mentioned this earlier, the breakdown that the machine learning doesn't work if the topology of your system changes. So if one element, like a line, is out, you actually have to have a model trained on that other topology. I think topology is the right word, to like resolve then. And I want to talk a little bit more about that, because for the first question, a changing energy mix, you're going to end up with a lot more instances of different and new topology, especially if you're trying to resolve this on distribution networks. So is this a solution if you have that constraint, or do we need to solve that constraint in this new and changing world? Anybody want to tackle the first question first? Is this more important in a world with new resources? Farhad has talked about it. Anybody else? Conleigh or Ahlmahz want to talk more about it?
What I'll say about your second question, so yeah, we do have to fix the fact that topology of your system changing shouldn't render the model useless. And when she was describing that problem, it felt a little bit like what happens when you overfit a model and then it doesn't work for anything else because you've just overfit a model. So stepping back and creating a machine learning tool that's able to give you a close approximation of an ACOPF solution, but is able to it's trained on multiple topologies, for example, or is able to consider the fact that the grid is dynamic. I think that has to be solved first.
Any other topics we wanted to dig into from Kyri's interview before we move on to our next segment?
I guess on the planning front, I thought it was a great point that, there's a lot of models out there right now that will use a very simplified representation of the grid, or even maybe no representation of transmission when thinking about future generation capacity expansion. And, one of the reasons for that is because it becomes really cumbersome. One of the reasons is because we think maybe that would change a lot in the future in ways that's hard to predict. But a big reason is that it's just computationally really difficult. And so it is an interesting idea that if you could, use more machine learning, AI techniques for having a higher fidelity model for some of these long-term planning situations, yeah, that could certainly be useful in the future.
Awesome. With that as the closing thought, let's hit the typewriter and check on the ESSA World Cup standings from the qualifying round. Okay, Kyri did not submit a new analogy yet, but she did vote on all of our existing analogies. So the top analogies remain in the lead. With the grid is like the human body, remains in first place, and the electric sector is like backcountry skiing, remains in second. The grid is like air, fell 4 spots from 3rd to 7th, which makes room for the electric sector as like a water catchment and irrigation system to come up to number 3. And the electric sector is like a game of Twister to move up to number 4, which is a huge moves because that was number 9. So it moved up 5 spots. Which it just does indicate that we're early in this tournament and you can get a lot of movement from single votes, or maybe something's wrong with the algorithm. Hard to say which. Okay.
I'm gonna say, never mind. Keep going.
Yep. Okay. I'm feeling really good about my electric utilities, or the PID controller of the electric system. It moved up to number 6. Number 7, the electric sector is evolving like the airs of Taylor Swift, is tied in 7th with the grid is like air. Okay, I don't usually reveal individual votes by voters, but I felt like it was a good indication of how the algorithm is working. The grid is like an old reliable car. It was actually her top ranked analogy. And it comes in at number 9 because of the incumbency advantage that is benefiting the grid is like the human body, and the electric sector is like backcountry skiing. So we're doing great. We aren't going to update any analogies this week to save time, but any commentary about how awesome the algorithm is?
No, we're going to introduce a weighting to adjust for this unfair advantage. Yeah, I need to look at your algorithm, Paul.
The algorithm does need some work. I'm not gonna lie.
It's all right. We're gonna come up with a weighting to adjust this.
Yeah,
no, it's boosted my analogies, so I'm happy with it. I don't see anything wrong with it at all.
I'm surprised by the meteoric rise of Twister, but I'll take it.
Yeah, it was meteoric. I was also surprised by it when I ran the numbers. But
I feel like your Taylor Swift is due for a bump. I mean, your assessment, and it was like, I think you should submit that to a paper, journal paper or something like that, because that was just that's due for a bump, surely. And if you open it up to the public, maybe that's we need to have a voting, public voting kind of thing as well.
That's a good idea. You know how MVP race for the NBA has a public vote component? We could have a public vote component for the ESSA World Cup standings. And I do think it's inevitable that the Taylor Swift analogy is going to keep rising in the rankings. It was a great analogy. In the next episode, we'll have a discussion of California burning with Catherine Blunt on the fall of Pacific Gas and Electric and what it means for America's power grid. You did see, obviously, we had a bonus episode just about Taylor Swift eras and how it relates to electric sector eras and how Pacific Gas and Electric history falls into those eras with Catherine Blunt, which got distributed as a bonus episode on April 19th, the same day as the release of Taylor Swift's latest album, The Tortured Poets Department. So we got that out today. But we also had a very informative and good discussion with Catherine separately, which we'll include in the next episode, and we'll talk about fire risk and infrastructure investments necessary for the transition and lessons to be learned from Pacific Gas and Electric for all of us electric utility and energy enthusiasts. But before we close it out, I hope you all feel seen, heard, valued, and appreciated. Ahlmahz, do you feel appreciated?
Absolutely.
Okay, we're gonna collect tips so that you can get an internet connection that's a little bit better, and we'll figure out from there. Farhad, it's Saturday morning in Australia, and you're here with us recording a podcast. Do you feel like you've gotten the appreciation for doing that for us?
Nothing I'd rather be doing. So, yes.
Thank you so much. Thank you so much for doing it. And Conleigh, do you feel seen, heard, valued, and appreciated?
Yes, thank you.
Thank you. Thank you for bringing your brilliance to this recording. I really appreciate it. Special thanks to today's presenting sponsor, the Energy Authority, for making this show possible. If you want to feel seen and heard, try tea. To our listeners, while you aren't seen or heard, you are valued and appreciated. Roll on, enthusiasts. Roll on.
We started in hard times to bring us all into the laughter through thick and through thin for public power enthusiasts without end.
Public Power Underground is a production of News Data and Seattle City Light. You don't have to be subscribed to News Data's weekly newsletter to get this podcast, but it sure makes the podcast make a lot more sense. The views expressed here are our own and not the official views of Seattle City Light, Tacoma Power, S&P Global, News Data, or the organization of the guests also appearing on Public Power Underground. I never include Harvard in there because you're an academic, so we just assume that you like you're just your own thing. It's the wonders of being an educational institute. Today's episode was written and produced by Paul Dockery, Ahlmahz Negash, Conleigh Byers, and Farhad Billimoria, and it's edited and published by the stellar team at Pioneer Utility Resources, with sound mixing by Lucas Smith and video editing by Brendan Delzer. Our theme song, Roll On Enthusiasts, was rewritten, performed, and recorded by Aaron Guillory and Ian Bledsoe. You can find Public Power Underground on YouTube, Apple Podcasts, Spotify, or your favorite podcast app. Please share with energy enthusiasts in your life and give us a rating and review on your app of choice if you enjoyed the content. It helps other energy enthusiasts like us find us. Public Power Underground for electric utility enthusiasts. Public Power Underground, it's work to watch.